In this video, we're going to be discussing Gauss-Jordan elimination. Now, Gauss-Jordan elimination is a further reduction of a matrix to a reduced row echelon form. So it's just like normal Gaussian elimination, except now we're going to be aiming to get it into reduced row echelon form instead of row echelon form. And to remind you, reduced row echelon form, for example, in this matrix, what we're trying to get it to be is we're trying to create an augmented matrix to the form, let's say for this one, we would have 1, 0, 0, 0, 1, 0, 0, 0, 1, and then some numbers here. We'll call them A, B, and C. So that's what we're trying to actually get to, all right, or something close to that. But really this. That being said, here, what do we get to start out with? Well, we have 1, negative 1, 2, negative 2, 3, negative 5, 3, 0, 5, and then 9, negative 4, and 17. All right. Well, we notice that actually, so this is actually, if you go back and look at prior videos, this is actually a previous example we already worked, and we were able to get it down to, so I'll say previous example. And we actually got it down to 1, negative 2, 3, 0, 1, 3, 0, 0, 1, and then 9, 5, 2. So what's left? Well, this is in row echelon form, but to get into reduced row echelon form, we need to make zeros there and there and there. So the first thing we're going to do is we're going to create a 0 here, and then we'll create the zeros there. To create the 0 there, what we're going to go ahead and do is, to our matrix, we're going to go ahead and add 2 times the middle row to R1, to row 1, and that'll create a 0 there. Doing so, we get 0 times 2, which will give me, just adding to 1 is 1. 2 times 1 creates a 2, thus canceling that out, which is the whole point. And then 3, and then if we do 2 times 3, we get 6. 6 plus 3 is 9. And then finally, 2 times 5 is 10, so we get 19 there. And then, of course, the rest of the rows stay the same. All right. And now what we're going to do is we need to make those 0. We're going to go ahead and do 2 row operations at the same time to do so. First, we're going to go ahead and take, we're going to be using the bottom row to do this. So we're going to get, give me a moment. We're going to take 3 times row 3 and add it to row 2, or to row 2, sorry, and that should be up here, to row 2. I'll write it that way. To get a new row 2, and then to get on row 1, to get rid of the 9, we're going to do negative, so that was negative 3. We're going to do negative 9 times row 3, add it to row 1. Doing so, we'll have 1 and 0, because adding the zeros to these don't change anything. 0, 1, 0, 0. The bottom will stay the same. And what do we get in the top? Well, here we'd get a 0 and a 0. And then we're taking negative 3 times 2, which is negative 6, added to 5 is going to give me a negative 1. And finally, here, when we take negative 9 times 5, we're going to get negative, when we take negative 9 times 2, we'll get negative 18, add that to that, and you get a 1. All right? And what is the advantage of this? Well, the advantage of this is now we have x equal 1, y equal negative 1, and z equals 2. So we're able to just read them off because that's x equal 1, that's y equal -1, and z equal 2. And so doing a few more steps with Gauss-Jordan elimination, we're able to get a solution, just read it off without back substitution. So this is our solution. And now it's time for you to try an example. So go ahead and use Gauss-Jordan elimination to solve the following system. On the count of 3, I will reveal the solution. 1, 2, 3. And here you see we went ahead and did the process in full. If first we swapped the top and bottom, and then I start doing a little bit more complex of row operations. But going through, the idea is I'm trying to avoid fractions, and so I kind of have to be a little bit creative with them. But going through, I eventually get it down to reduced row echelon form here. And so I'm able to read off the entries, which are 7, 4, -3. And I even went ahead and checked the entry and checked my solution as well. Let's do another quick example. Let's go ahead and solve the following system of equations. Here, our augmented matrix would be 2, 4, -2, 0, 3, 5, 0, 1. Here we want to row reduce. Let's go ahead and multiply the top by 1/2, the top row, since everything's divisible by 2. So 1/2 R1. So we'd have 1, 2, -1, 0. In the bottom we still have 3, 5, 0, 1. Which is, we have, if we go ahead and, if we add, let me create a bit more room here. If we go ahead and we do -3, if we do -3 times row 1 and add it to row 2, then we would get a 1, we'd still have 1, 2, -1, 0 there. But in the bottom row, we'll have a 0 there. -3 times 2 is -6, plus 1 is -5, is -1. And then I would have 3 plus, I'd have -3 times -1, which is +3, added to 0 is +3. And then -3 times 0 is 0, added to 1 will be 1 still. All right. And now, because I almost have a 1 here, I'll go ahead and multiply the bottom row by a -1 times row 2, which will give me 0, 1, -3, -1. The top, of course, stays the same. And now, to get this into reduced row echelon form, I just need to make this a 0. Okay? Making that a 0, I'm going to go ahead and multiply the bottom by -2 and add it to the top row. So -2 row 2 added to row 1 to get a new top row, which will give us 1, 0. -2 times -3 is +6, so plus a -1 is +5. -2 times -1 is +2, so I'll get a 2 up there, add it to 0, and then this stays the same. Which now we have this in reduced row echelon form, which means we can read this off. This is x plus 5z equals 2, and y minus 3z equals -1. Not surprisingly, because we had more variables than we did equations starting off, namely we had 3 variables but 2 equations, we kind of expected this. So we have an infinite number of solutions. We'll go ahead and let z equal some constant real number a. Doing so will give us that x is equal to 2 minus 5a, and y will equal 3a minus 1, using that equation. And so, in other words, we have 2 minus 5a, comma 3a minus 1. And then we have a, right? So for a, any real number. So that'll be our solution. Now it's time for you to try an example. So go ahead and try solving this system of equations. On the count of 3, I will reveal the answer. 1, 2, 3. So here, very similar to the last example, you end up with x minus 3z equals 8 and y minus 2z equals negative 5 once you've done Gauss-Jordan elimination. We go ahead and we pick our a, and we end up with this as the solution. For more practice in solving equations with Gauss-Jordan elimination, be sure to see pages 551 and 552 of the textbook. In our next video, we will be discussing equality of matrices.